So now we're in section 3.4. If you recall, 3.1 was measures of center, 3.2 was measures of dispersion. We're going to omit 3.3. It's a fairly interesting section, but we don't have time to cover it. It's not on our list of objectives. And so now we're in 3.4. It's called measures of position and outliers. We're actually going to do 3.4 and 3.5 in this video because they're connected. It could easily be just combined into one section, and that's what I'm going to do here. It's a fairly easy section. I think it's easier than standard deviation. And so let's move forward. We have 4 objectives, actually 5 objectives, excuse me. We want to talk about something called z-scores, which will be important. Percentiles, again, important. Quartiles, important. Interquartile range, important. Outliers, important. Sometimes some of these objectives have more importance than others, but in this particular section, 3.4, all 5 of these are important for our purposes and for the future. Objective 1, determine and interpret z-scores. A z-score just tells us how many standard deviations away from the mean a data value lies. Let me explain. So if you have a distribution with a mean of 100 and a standard deviation 10, then the z-score for the value x equals 110 is going to be 1. Why? Because it's 1 standard deviation away from the mean. Look at this. The distance between 110 and 100 is 10 units. And then 10 into 10, 10 here divided into 10 is 1. So it takes 1 standard deviation to move from 100 to 110. This is the z-score underlined here in the lower right. What you want to understand is, again, redundantly, a z-score is very important because it will tell us a position of a data value in terms of how many standard deviations it's either above or below the mean. When your z-score is negative, it means you're below the mean. When a z-score is positive, it's above the mean. You have 2 formulas here, but they're essentially the same formula. And what that means is your z-score, you see here I'm circling with my cursor z, that's the z-score, equals the distance between the data value x and the mean, but then divided by the standard deviation. What it is you want to see how many times the standard deviation will be divided into this distance, and that tells you how many standard deviations the data value x is away from the mean. This formula on the right for sample z-scores is conceptually identical, meaning in the numerator you have the distance between the data value given and the mean of the sample, and it's divided by the standard deviation of the sample to see how many standard deviations go into this distance. Make sense? All right. Notice here, if x is below the mean, the subtraction will be negative, and therefore your z-score will be negative. The same over here. If x is less than x bar, the subtraction will be negative, and your z-score will be negative. However, on the other hand, if your data value is above the mean, the subtraction will be positive, and then your z-score will be positive. The z-score is unitless. It has mean 0 and standard deviation 1. Don't really worry about this right here. This will be important when we get to chapter 7 when we talk about something called standard normal. All right, this last sentence right here about the mean being 0 and standard deviation 1, this will not be important to us until we get to chapter 7. All you have to do right here is understand that the z-score is unitless. It just tells us how many standard deviations it's required to move above the mean to get to a data value, or how many standard deviations it's necessary to move below the mean to get to a data value. This is a really nice example. I put this on tests a lot. And so we want to view this as 2 separate populations, a population of males and a population of females. For males, the mean for the distribution is 69.1 inches with a standard deviation of 2.8. For the females, all right, the mean is 63.7 inches with a standard deviation of 2.7. We have 2 very tall people, both Kevin Garnett and Candace Parker. Kevin is 83 inches tall, Candace is 76 inches tall. Obviously, Kevin is taller than Candace, but that's not the question we want to ask ourselves. We want to know who's taller relative to their respective populations. So, is Candace taller as a woman than Kevin is taller as a man, or vice versa? What we do is we convert to z-scores. One of the things I want you to notice here is see the subscript on the z-score on the left and the subscript on the z-score on the right. It's really important that you use good notation so you don't lose track of what you're doing. So this is the z-score for Kevin and this is the z-score for Candace. It's really important to use correct notation, all right, to keep, because as a human being you have a tendency to make mistakes, and so this is just a way of helping us prevent those types of mistakes, those confusion errors. Anyway, we have the data value, Kevin's height, 83, minus the mean for the distribution divided by the standard deviation, and he gets a z-score of 4.96. What that means, technically and formally, is that his height is 4.96 standard deviations above the mean of 69.1. Then we compute Candace's z-score for her population, females, and we see that the data value, her height, minus the mean for the distribution divided by the standard deviation of the distribution yields a z-score of 4.56. And so because Kevin is almost 5 standard deviations above his mean, whereas Candace is only about 4.5 standard deviations above hers, then Kevin is taller in his respective population, meaning he's taller as a male than Candace is tall as a female. Think about this. This is a really important example because, again, I put it on the test a lot. So now we're going to talk about percentiles, but I'm going to warm you up to that idea of percentiles by starting with the idea of the median. The median divides the data set, the distribution, into two equal parts, 50% below and 50% above. Okay. But it's always misleading when you draw a picture like this and you start throwing out that term equal parts. What I mean by equality is there's 50% below and 50% above. If this left-hand mark where I'm pointing the cursor right here represents the low score, the minimum, and this mark right here represents the maximum score, it does not mean ever that the median has to be exactly in the middle with respect to distance. What it means is the median divides the data set up so that you have 50% below and 50% above. It's possible that the bottom 50% are all compacted in this little space here, whereas the top 50% are spread out along this longer line. Okay. If we divide the, and we'll talk about quartiles in a few minutes, it's one of the objectives. If we divide the distribution into 4 equal parts, equal in the sense that not distances are equal, but 25% of the data values, 25%, 25%, 25%, 4 25% segments, then those are quartiles. Like quart of milk is a fourth of a gallon, quartiles. If we divide it up into 5 equal parts, 20%, 20%, etc., those are quintiles. If we divide it up into 10 equal parts, deciles, all right? And if we divide it up, back to our objective, when we divide it up into 100 equal parts, percentiles. This is copied from Wikipedia. The reason I have this slide here is to emphasize that if we want to be technical and get into all the details of this, it can be extremely confusing, all right? But there's a very simple and intuitive explanation that I need you to understand, and I don't really need you to understand all the complications and details. They can get overwhelming. But there's a very intuitive and easy to understand explanation that we'll see on the next slide. What you have to understand is we have this notation, P for percentiles. We're dividing the data set up into 100 segments. All right. This number, P98, is a number on the x-axis, the horizontal axis, such that, now listen to this, this is important, such that 98% of the data values fall below that mark. All right. If I'm at P2, that means 2% of the data values fall below that mark. If I'm at P99, that means that 99% of the data values fall below that mark. The main thing to remember is this number indicates what's to the left. What's to the left. So here, the 70th percentile, that means that 70% of the scores are below that mark. Okay. And so you can slow down and read this example. Okay. But I think I've explained percentiles well enough. But 70th percentile means that 70% of the data values are below that score. Determine and interpret quartiles. Now we've already done that, but so this should be easy. We divide the data set into 4 equal segments containing 25%, 25%, etc. The one thing I want you to focus on very carefully here is that this picture is misleading. I have a tendency to do this on the board. All textbooks have a tendency to do this. These diagrams are very misleading. We're not talking about equal distances. We're not talking about equal distances. What we're talking about is 25% of the data, 25%, 25%. Okay. Technically, there is no such thing as the second quartile. The median is the second quartile. 50% below, 50% above. On an intuitive level, what Q1, the first quartile, is just the middle between the minimum score of the data set and the median. If we divide this up in half so that I get 25% here and 25% here, this Q1 is essentially the median of this bottom 50%. In a similar manner, Q3, the third quartile, is nothing more than the median of this top 50%. You'll never be asked to compute quartiles by hand, but you will be asked to conceptually understand them, and you will be responsible for the names, first quartile, third quartile, etc., and you will be responsible for the symbols. So here they're explaining how to find quartiles, but we're always going to use technology to do that. So now we have the fourth objective, determining and interpreting the interquartile range. Whenever we use the mean as our measure of center, then we always, without exception, use standard deviation as our measure of dispersion. Whenever we use the median, remember sometimes we switch from the mean over to the median as our measure of center. Whenever we use the median as our measure of center, then we use something called the interquartile range to measure the dispersion. The reason being is the median is resistant, but the mean is not. And in a similar manner, the standard deviation is not resistant to extreme values, but the interquartile range is. The reason being is all you measure is the spread of the middle 50% of the data. 25% here, 25% here. What's happening is any extreme scores that you have, either on the high end or on the low end, get eliminated in the calculation of the interquartile range, because all you do is you just look at the distance between Q3 and Q1, and you don't even look at what's out on the extreme ends. So this is extremely easy. Interquartile range, abbreviated IQR, is just the distance between the third quartile and the first quartile. You can look at these examples if you want, but this is very, very easy. So to reemphasize, whenever our distribution is roughly symmetric, we use the mean for our measure of central tendency. And whenever we use the mean as our measure of central tendency, we always, without exception, use standard deviation to measure dispersion. But if the data value is skewed left or right, because the mean is not resistant, we use the median for the measure of central tendency. And anytime we switch from the mean to the median, then we switch from standard deviation to interquartile range to measure dispersion. The mean and the standard deviation are preferred methods for center and spread, but if we have skewed data, that skewedness distorts the value of the mean and standard deviation because they're not resistant, and we switch over to the median and interquartile range. So now our fifth objective is to check a set of data for outliers. Outliers are extreme scores. And in order to determine if something is an outlier, you have to compute something called fences. Now, you know what this symbol is here, right? It's the first quartile. And you know what this symbol is right here. It's the interquartile range. And so the very first thing you do is you compute Q1 and Q3. All right, you'll use technology to do that. Once you have Q1 and Q3, compute the interquartile range, which is just Q3 minus Q1, and then compute this calculation. Q1 minus 1.5 times the interquartile range, and Q3 plus 1.5 times the interquartile range. Any number that's lower than the lower fence is an outlier. Again, outliers are extreme values. Any number that's greater than the upper fence is an outlier. That's what it's saying down here in step 4. So let's look at a specific example. I have a data set. Okay, the first and third quartiles are 28 and 38 respectively. Okay, the interquartile range is obviously 10. So the lower fence is Q1, this 28, minus 1.5 times 10, which is 15, so 28 minus 15 is 13. The upper fence is Q3, the 38, plus the same number that we used up here for the subtraction, so 38 plus 15, which is 53. Then we look at the data set. Any number that's smaller than 13 or bigger than 53 is an outlier, meaning it's large, very large. It's away from the rest of the data set. There are no values less than 13 or greater than 53, therefore there are no outliers. What's happening here is you don't necessarily have outliers, or you could have them on the left and not on the right, or on the right and not on the left, but anything that's either smaller or bigger than your fences, those are outliers. So now I'm on 3.5. This is all connected. We have two objectives talking about something called a 5-number summary and something called box plots. The 5-number summary we'll do first. It's so easy. It's like ridiculously easy. If I give you a data set, do you know what the lowest value is called? It's called the minimum, right? Do you know what the largest value is called? It's called the maximum. What does capital M mean? The median. What is Q1? The first quartile. What is Q3? The third quartile. These 5 numbers, the minimum, Q1, the median, Q3, and the max, the 5-number summary, and that's it, done. So now we're on drawing and interpreting box plots. For this concept, for this objective, you will necessarily need to remember the last objective in 3.4, which was outliers and fences. All right, we need that idea of fences here and outliers. So you compute the lower and upper fence. Let me just find a picture and then I'll draw it. You draw a rectangle. How is the rectangle drawn? This left end side right here, the bottom side, this is Q1. The top side is Q3. It doesn't matter how tall and short you make it. It's just sitting there above, floating above the x-axis. But the left-hand mark here, wherever the cursor is, that's Q1. The right-hand mark right here is Q3, and then you draw a rectangle based on those two lines. Then you draw a line through the box that designates where on the number line the median falls. And so 3 lines, Q1, median, Q3. Then you compute what the fences are. See here, the lower fence is 8.4, the upper fence is 18. Okay, so 8.4 is about right in here where the cursor is, right there. Okay, and 18 is way, way out here like this. Okay, mark anything that's an outlier. Where are these outliers coming from? From these data values right here. Okay. So I have one outlier way down here on the left, which is about 6.5%. Let's go back to the data set again. See the 6.5? That's our outlier on the left. But none of the values here are big enough for them to be outliers on the right. And so as you see, I have no asterisk or stars on the right, so there's no outliers. Then you have, finally, the concept of whiskers. This is a whisker. This is a whisker. How are the whiskers marked? This end of the whisker on the left is the smallest value inside the fences. Remember, the fence is 8.4, so the fences were out right in here. So this is the minimum value out here marked as an asterisk, as an outlier. So that means that this end of this right here, the end of this whisker right there, will be the second smallest value. If I had 2 outliers on the left, then this would be the third smallest value. If I had 3 outliers on the left, this would be the fourth smallest value. The end of your whisker corresponds to your data value from your table. That's the smallest value still inside the fence, the smallest value that is not an outlier. Over here, we have no outliers on the right, so this last whisker corresponds to the maximum value. If I had an outlier out here where the cursor is, just 1, then this would be the second largest value. But because there's no outliers on the right, this corresponds to the maximum. If you have no outliers whatsoever, none, then this lower whisker, right, will correspond to the minimum there, and the upper part of this whisker right here will correspond to the maximum. Smallest value that's not an outlier. Largest value that's not an outlier. So now we find, this is the last thing, we want to compare histograms to box charts and talk about the symmetry or skewedness of the situation. Remember that the middle, not the middle, but the line inside the rectangle, the line inside the rectangle measures the median. So median, median, etc. So we have 50% of our data from this line out to here, and 50% of our data from this line right here to the left to that mark right there. Notice how it's stretched out further to the right, and that's why we get skewedness to the right here. Here, the distance from the median to the end of the whisker, is about the same, so we have a symmetric diagram. Here, the distance from the median to the bottom whisker is much more stretched out than it is to the right. Therefore, we have skewedness. So to review, what are z-scores? Measure how many standard deviations we are above or below the mean. What are percentiles? It divides the number line up into 100 pieces, and if you're at the 78th percentile, that means 78% of the data falls below that mark. What are quartiles? They divide the number line into 25%, 25%, 25%, and 25%. All you have to do, you don't have to worry about calculating them. You just have to understand what they are conceptually, understand what the symbols are, and understand what these words mean, quartiles. Then you have to determine and interpret the interquartile range. Again, that's super easy, Q3 minus Q1. We always use the interquartile range when we're using the median as our measure of center. And then the other two objectives that we covered in 3.5, the 5-number summary. What was the 5-number summary? Minimum, first quartile, median, third quartile, and the maximum. Then we did box plots. And box plots are just a way of looking at the data to see if it's skewed or where the median is, where the quartiles are. But make sure you know how to draw one by hand. Make sure you know how to interpret one if you see it on a test given as a graph.